1.3 linear models. So we're talking about basically a linear equation, and we've seen some of this before. This should be familiar. Point slope form looks like y minus y1 equals m times x minus x1. That's point slope form. Slope intercept form, y equals mx plus b. That's the one we're most familiar with and most comfortable with. And then there's standard form, ax plus by equals c. We've seen these before, but it's going to get kind of intense today. Example 1 starts off with a familiar problem. Find a linear equation for the line through these 2 points. So in order to do this, we're probably going to want to find the slope. So remember the slope equation, y2 minus y1 over x2 minus x1. So when you look at these 2 points, y2 minus y1 over x2 minus x1, 10 minus 18 is negative 8. 30 plus 42 is 72. And we've got this messy looking fraction. It reduces to negative 1/9. So that is the slope. Now we'd want to, well, we can find the y-intercept, I suppose. So it kind of depends. Some people prefer to do slope-intercept form. I think point-slope form is kind of easier. So what I would do is I would use point-slope form, and I want to pick a point. I'm going to pick this one because I think it's easier. That's my x and my y. And I'm going to put my x and my y into this equation. Now, sometimes I'll look at this, and instead of saying y1, I'll say y number. And over here, instead of saying x1, I'll say x number, because that's where the number goes. That's where my 30 and my 10 are going to go. So this equation would be y minus my y number is 10 equals the slope negative 1/9 times x minus my x number of 30. So that's a linear equation. Technically, we're finished, I suppose. Find a linear equation. We've got one. But usually, you're going to want it in slope-intercept form. So that's usually what you'll do. You've got a couple of options here. Multiplying by 9 is nice because it gets rid of your fraction for a while. But we don't necessarily need to do that if we can handle the fractions. So let's look at distributing to get rid of the fractions here. I'm going to write kind of small because I'm about out of room. So y minus 10 equals negative 1/9 x plus 30 over 9. And yeah, I know that's an ugly fraction, but you're going to have to deal with fractions at some point. There's one. Get y by itself. So I would add the 10 over, add the 10 over. But when you add fractions, remember you add fractions, you need a common denominator. So we need a denominator 9 on that. 10 with denominator 9 is like 90 over 9. And so I would just think of 10 as 90 over 9 because that's going to be able, or I can add those fractions now. So this cancels. 30/9 plus 90/9 is 1/29. I get y equals negative 1/9 x plus 120 over 9. And other than the fractions, that problem should seem fairly familiar and comfortable to you. You've done that kind of thing a lot in algebra class, algebra 1, algebra 2. There it is again. But that's kind of a very basic example of what we're doing today with linear models. Finding a linear model through more than 2 points can be useful for making predictions, and that's kind of what we're trying to do today. So you see this scatter plot with a whole bunch of points, and you might try to come up with a line of best fit. You're trying to find a line that best represents all of these points. Now, you're not going to hit them all. You just have to try to find some kind of approximation that is as good a representation as you can possibly get, a line of fit. All right, draw a line of best fit through the data points. Okay, I just did it. It's a little crooked, but try to draw a straight line. And then predict the amount of business with 35 client contacts. So you can see direct client contact, 5, 10, 15. 35 is going to be like over here, right? So we want to know, where does this line, where does that line reach at 35? I don't know. It depends on how you drew your line, but it looks like it's about, I don't know, I'm going to guess 12,100. And that is just an approximation. I would have to do a lot of calculations to find it more accurate than that. But just based off that picture, 12,000, 12,100, something like that. So we've got a method. And the main method that you use to find an equation, like a precise equation, is called least squares regression. Least squares regression deals with something called residuals. Residuals indicate the accuracy of each point. Each of those points in that scatter plot. The least squares regression method is a way to find the line of best fit by looking at the lowest possible value of the sum of the squares of the residuals. Okay. So what in the world does that mean? So you look at this, and I've got the same scatter plot drawn 3 times, but I've got 3 different lines drawn through. And so the question is, which of those 3 lines best represents those dots? And it's hard to tell by looking. And so that's why you've got this kind of complicated calculation going. But we're going to look at the residuals for this. And what the residuals are is kind of like how far this dot is off this line. All right. So that would be, we're going to call that negative 1.7. And this dot is right on the line, so we're going to call that 0. It's 0 away from that line. And this dot is, we're going to call that negative 0.7. Anything that's underneath the line is a negative. Anything that's above the line is positive. So that's why this one is going to be positive 1. And this one is going to be negative 1.7. And this one's right on the line, so we'll call that 0. Okay, so least squares regression, we're taking the sum of the squares of those residual numbers. And that's what's happening right here to get to this number. All right, so 7.27 is an approximation of the sum of those residuals. By the way, you better get used to this symbol, sigma. It's the Greek letter sigma, and sigma is talking about sum. Anytime you see the Greek letter sigma, it's adding things up. It's the sum of whatever they're talking about. Okay, so this one we've got negative 0.5 and 1 and 0 and 1.5 and negative 1.5 and 0. And so we add up all of those residuals, sigma e, and we get this total. And then over here, negative 0.93, 0.6. By the way, there's no way we would know these numbers for sure. I made the example, and that's why I know what these numbers are. And this one's off just barely, negative 0.13, and this one's positive 1.46, and negative 1.3, and 0.26. So we find the sum of those residuals and find 5.3. So the name of the game is least squares regression. So we're looking at the lowest possible value of the sum of the squares of the residuals. So we're looking for that lowest number right there. That lowest number, 5.3, tells me that that third line is actually the best fit out of those 3. It's hard to tell when you're looking at it, but that's why we have to do some kind of calculations. All right. Also, when you think about squares, you could kind of draw squares right here and think of it like we're trying to minimize the area of those squares is what we're doing. All right, the best fit line is the one that's going to minimize the area of those squares. I know that's tough to understand, but the good news is we won't really have to do that. I'm just trying to tell you what is happening and why it's happening. So we're looking for that lowest value. We're looking for the least value of that sum of the squares. The correlation coefficient R is a value between -1 and 1. R indicates the correlation between the x variable and the y variable. And you may remember this from algebra class, but positive R values show a positive correlation, and negative R values show a negative correlation between the two variables. And a positive, it's kind of like slope. When you see a positive correlation, the line goes up. And when you see a negative correlation, the line goes down. But basically that means a positive correlation is when one goes up, the other one goes up. And a negative correlation is when one goes up, the other goes down. And so let's see. If I had an example of I'm selling ice cream and I'm looking at my ice cream sales compared to the temperature outside, you can think about when the temperature goes up, my ice cream sales are going to go up. That makes sense, right? As one goes up, the other goes up. That's a positive correlation. But if I'm a wool mittens salesman, as the temperature goes up, my mitten sales are going to go down. That would be a negative correlation, okay? The closer an R value is to 1 or -1, the more closely the data resemble the line. So we're looking for an R value that's near 1. An R value of 0 shows no correlation. R squared is just what it sounds like. It's this R number squared, but it's going to be a value between 0 and 1. And that's the number that's going to be easier for us to come about because I'm going to show you how to do this using a web calculator, and it'll give you the R squared number. So R number, R squared number, both of them are basically telling me how well the linear regression model fits the data. All right. The closer the R squared number is to 1, the better the fit. All right, the better the fit. So when you look at these pictures down here, R squared equals -1 tells me a couple things. Oops, R equals -1. If you square that, -1 squared is 1. So the R squared value would be 1. And that's perfect. That's a perfect fit. And so what that means is my line or my equation perfectly fits the data points. That won't always happen. That seldom ever happens. But the negative, the R being negative just tells me that it's a negative correlation. It's a negative slope. So then the next one, R equals 0, that means there's no correlation, and I have no idea how to draw the line. I don't know if it's uphill, downhill, flat. I don't know what it looks like. You can square that and find R squared equals 0. But that's just an indication that it's a terrible fit. There's no correlation. I have no idea. The next one, if you squared it, R squared equals 1. That's perfect again. Since R is positive, it tells me it goes uphill, but that's a perfect fit when R squared is 1. So then these are a little bit more realistic. You see some scatter plots, and you can see the lines are not perfect representations. Which one is the best representation? The first one, second one, or third one? The third one, because it's R squared is going to be closer to 1. Okay, when it's closer to 1 or closer to -1 or farther away from 0, I guess, the farther it is away from 0, the better the fit. And you can see these points right here are pretty tightly compacted around the line. That's a pretty good fit. But we really want it closer to 1 or closer to -1. By the way, if you squared this, R squared equals 0.25. If you squared this, you'd get 0.49. If you squared this one, you get 0.7225. Ideally, we'll have higher numbers than that because we want those R squared values closer and closer and closer to 1.